Hello everyone, welcome to cheme.friends. I am Akshay and today we'll be taking a look at cracking of acetone using a steady state non-isothermal plug flow reactor. And if you have never done ordinary differential equations on MATLAB before, I suggest you click on the card above and solve a relatively easy batch reactor system. And if you want to take a look at the question, you can check the description box below and the link is present there. So let's begin.
So let's read the question. We have an irreversible vapor phase cracking reaction of acetone, which is represented by A, to ketene and methane, which is represented by B and C respectively, is carried out adiabatically in a plug flow reactor. And the reaction is first order with respect to acetone, and the reaction rate is given by this. Okay, so this is a standard first order reaction. We have a rate constant, which is a function of temperature, it's given. And for a gas phase reactor, the concentration of acetone is represented by this equation. So this is a component balance on the ideal gas equation. You can derive this very easily. And the enthalpy of the reaction is a function of temperature and it's given by this. All right. And yeah, the specific heat capacities of A, B, and C are also given. So the acetone feed flow rate in the reactor is 800 kilogram per hour, which is equal to 38.3 gram mole per second, and it's also the max capacity for the inlet of the reactor. The initial temperature is also given, and the reactor operates isobarically at 1.6 atmosphere, and the volume of the reactor is 4 meter cube. So we have been given three parts to the second question. So the first question is pretty straightforward. We have to calculate the flow rate and the mole fraction of each species at the reactor outlet. In the second part of this question, we have been given that in order to increase the conversion of acetone, it's suggested to feed nitrogen along with acetone, and the total molar flow rate is supposed to be maintained at 38.3, just like in the previous case. And we have been given different inlet flow rates for nitrogen, and we have to check what the conversion would be, and we have to plot the results as a function of reactor volume. So we have also been given the specific heat capacity of nitrogen as a function of temperature, which we will be using on later. And in the third part, we have been given that we have to calculate the final conversion and temperatures in the reactor operating at a pressure range between 1.6 atmosphere and 5 atmosphere, and different feed rates of acetone have been given. So the total N2 plus acetone should be equal to 38.3. So that's one thing we need to keep in mind. And the inlet temperature has also been changed in this case. As we can see, it's 1035, whereas in the previous cases it was 1150. We have to plot the final conversion versus pressure as well as the initial flow rate. Also, the second plot, this would be first plot, and the second plot will be to plot the final temperature versus pressure and flow rate. So this is a basic representation of our question. We have been, this flow of nitrogen into our system is an optional. So we have acetone, which will give products ketene, methane, and some amount of unreacted acetone. So we've already discussed our methodology, and it brings us to part 2 of our methodology, which is to define the initial value of the problem. So we have three parts in this question number 2, and let's discuss it one by one. So in the first part, we have the initial flow rate of A as 38.3 mole per second, whereas the second two components are not there yet because the cracking reaction takes place inside the plug flow reactor, and the initial temperature has been given. It's isobaric condition. It is at P equals 1.6 atmosphere. Whereas in the second case, we have the flow rate of A depends on the mole flow rate of nitrogen. We have been given several cases of nitrogen flow rate, so we will be doing it one by one in our code. And again, no reaction has taken place prior to the feed entering the reactor, and hence no flow rate of B and C. And again, the temperature is 1150 Kelvin. Same case with the pressure, it's the same as in the previous case. Whereas in the third case, we have Again, we have the total sum of A and nitrogen is equal to 38.3, and the flow rate of B and C initially is 0, and this in this case we have a different temperature at the inlet, and we have been given it is at isobaric condition, but we have to find different cases, and we have to find out what's the conversion at different pressures in this range. So let's move on to the next part. In part 3 we have development of the mathematical model, and as you have already seen in the question, we have concentration as a function of temperature, and the pressure is constant, so it will mainly depend on the temperature. The pressure is in kilopascal, and hence the value of 1000 as the constant. Temperature is in Kelvin, and the universal gas constant is in joule per mole Kelvin. The conversion, as we all know, is equal to the initial flow rate in minus the final flow rate divided by the initial flow rate, and we have already derived the design equation for a PFR. It's these three equations for each of the reactant and product respectively, and this is the component balance for the system, and we'll call it equation 2 for the time being, and this is equation 1, of course. Let's move on to energy balance for the system. So similar to the material balance and mass balance that we did in the previous section, we have a representation of PFR, and we will again consider a differential volume dV, and prior to entering this differential volume we have flow rates FA, FB and FC, which are the flow rates of the respective components, and enthalpies HA, HB and HC before entering the differential volume. And when these components exit this differential volume, we have FA plus FDA, which represents the change in flow rate after the component exits this differential volume, and similarly we have FB plus DFB and FC plus DFC. Now since there will be a change in temperature within this differential volume, we also have the enthalpy, which is a which is a function of temperature. So there will be a change in enthalpy of these components as well. So we have DHA plus HA, and similarly we have DHB plus HB and DHC plus HC. So let's move on to the energy balance. We have energy in minus energy out equals accumulation, and since t tends to infinity we have a steady state system, so we'll be assuming steady state conditions in this case, and there won't be any uh, heat flow rate outside the system due to the conditions being that it's an adiabatic system. So the energy in will be equal to these three terms which we saw in the figure. So this will be energy in, and similarly the energy out will be equal to these three terms. So in step 3 we will manipulate these and cancel some terms, which is FAHA, which are common in these equations, so we will be cancelling it out. And in step 4 we will divide the entire right hand side and left hand side with the differential volume dV. Okay, and let's discuss this bracket first. Since we are multiplying a small value into whatever value we are when we multiply a differentially small, infinitesimally small value into however big the value is, this value will be equal to 0, and hence this entire bracket will be 0. All right, and we have to see what we can do with these cases. So in step 5 we will see that we know that the values of dFA by dV from our design equation, and we'll call it A, and we also know that the enthalpy of rather the specific heat capacity Cp for a component is equal to the enthalpy of that component, the change in enthalpy of that component with respect to temperature at constant pressure. And we know that these conditions are satisfied in our case, and hence when we substitute values from A and B, we get this equation. And we know that the delta H of the reaction is given by the enthalpy of the product minus the enthalpy of the reactant, right? So these terms give the delta H of the reaction, and when we take dt by dv common from the previous equation in this term, we finally obtain the change in temperature with respect to with respect to volume is given by the product of rate of reaction to the change in enthalpy of the reaction divided by the flow rate and the specific heat capacity, the sum of flow rate and specific heat capacity of all components within the system. So in parts 2 and 3 of this question, we also know that N2 is involved, and we can easily derive that an additional term will also be present in the energy balance of this equation. It's easy to derive. It's similar to how we derived equation number 3. And equation 4 here is more generalized for our case. So let's write the system of ordinary differential equations again. So we have these three equations which are the component balance slash design equation for a plug flow reactor, and we have this equation which we derived just a few seconds back, which is the energy balance, and we'll call it equation 4. But while we write these down, we should also keep in mind that we have specific heat capacity, which is a function of temperature. We have rate constant K of the reaction, which is also a function of temperature. We also have the enthalpy of reaction, which is also a function of temperature, and we also have the concentration of A, again a function of temperature. So we need to take all this into consideration while we write our differential equation in our MATLAB environment. And this, let's move on to the next part of our problem. So the next part of our problem is inputting all these differential equation into our MATLAB and getting some results out of it. But before we begin to start writing our code, we will first decide a basic schema of how things will work in our MATLAB environment. So we will write three M files for each question, question 1, question 2 and question 3. Pretty straightforward, right? And what's common in all these three M files will be that we'll have a function which will define our differential equation. We'll call it diffpfr, and the arguments for this differential equation will be the concentration, temperature, pressure, and the nitrogen flow rate, which we'll get from question 1, question 2 and question 3. As we all remember that these things are different in each question, but what's common is that we have a system of differential equation that's common between all these three equations. So let's move on to the MATLAB environment, and we'll see every question one by one. So we have come to the MATLAB environment where I have made a function called diffpfr, and the arguments are volume x, which we will see what it is soon, and pf. So x is a column, rather a row matrix, which where x1 represents acetone, the flow rates of acetone, x2 represents the flow rates of B, and x3 represents the flow rates of C, and x4 is the temperature along the reactor volume, right? And pf is a small row matrix which has the pressure in the PFR in PF1, which is the first index, and the flow rate of nitrogen in the second index. So we'll define P equals PF1, which is the pressure of the PFR, and Fn2 as PF2, as already discussed that it PF consists of both the pressure as well as the flow rate of nitrogen, and T equals X4, which is the temperature which is a temperature, and we are defining R, universal gas constant, and we are writing Ca equals the equation that we have already discussed, the concentration of A as a function of temperature. We are writing the rate constant as a function of temperature, and we are writing the enthalpy of reaction as a function of temperature, Cp, Cb, Cc, and the specific heat capacities of all these components as a function of temperature, and defining Ra as minus K into Ca, which is the rate of the cracking reaction. And finally we get the output. We are writing a column matrix where minus Ra is the right hand side, rather the plus Ra is the right hand side of equation 1, minus Ra is the right hand side of equation 2, again this is the right hand side of equation 3, and we have the right hand side of the change in temperature with respect to volume. So this is the, so we define this as dy dx, and if you can see in the function definition, we know that the output dy dx, which is this matrix, is the output for the entire function file.
So the function that we have just written consists of all the ordinary differential equations which will be required to solve future parts of this question. So make sure you understand it. So let's move on to the next part.
So I have already made the solution of the first M file, which is question 2 part 1, and part 1 is arguably the easiest among the three parts. So let's first discuss the easy part of question number 2, and so we are defining PF as we have discussed while writing the script for the diff PFR M file, which is the function containing the differential equations for the PFR system. We have 162, which is the pressure in kilopascals, and we have no nitrogen flow rate in the first part and hence 0. We have volume range, which is line space of lin space between 0 and 4. Our volume ranges from 0 meter cube to 4 meter cube. It's given in the question, and we are dividing it into 100 parts. And the initial values are already given, which is the initial flow rates of acetone is 38.3, and the rest is 0, and the fourth value of this vector is 1150, which is the temperature in Kelvin. So we are writing V comma X equals ODE, let's write 45, and we are calling the function diff.pfr. So if you remember, we made this function diff.pfr previously, and we are calling this function. We are writing the volume range between which we want to integrate this function and the initial values. We are not putting anything in the options. ODE 45 or any ODE as such allows us to apply some additional conditions like stopping at the minima, etc. So we are leaving it empty as of now, and we are writing the additional arguments which are required for diff PFR, which is PF. So in this code we are just going to be displaying the flow rate of acetone at the end of PFR. So
Okay, so we
again,
have come
let's
to the
see what
explanation of
line number 5 of our code
line number
means.
5 of our code. So we have this ODE function, we are calling it the differential equation file, etc. So we are creating two matrices, basically V and X, and X is the flow rate of A, X2 is the flow rate of B, X3 is the flow rate of C, and X4 is the temperature in Kelvin. So when we integrate this, when we call this function, what we are basically trying to say is I want a column vector consisting of 100 divisions, as we saw in line space, between 0 and 4, and we will be finding the corresponding flow rates. At V equals 0 we have 38.3 gram mole per second, and similarly we will be plotting like this and obtaining our final values for flow rate of A at 4 meter cube, flow rate of B at 4 meter cube, flow rate of C at 4 meter cube, and temperature at 4 meter cube. So that's what we are obtaining from line 5 of the equation. Now these lines will be displaying the flow rates of each component and the mole fraction of the respective component as asked in the question, and we also have the temperature at the end of the PSFR which will be displayed. Let's run this code now. So I'll click on run and let's see what we get. So okay, so flow rate of acetone at the end of PFR is 19.97, and the mole fraction is this, and as we know, cracking reaction is endothermic in nature, and the temperature has decreased from 1150 to 920.8 Kelvin. So let's move on to part 2 of the question. Okay, so this is the code for the part 2 of the question which I've already made for you guys. So we have made a we have made an array for nitrogen feed, which is already given in the question. There are 5 cases, and we will be creating a loop so that through each loop we'll be varying the nitrogen flow rate, and we'll obtain the mole fraction for each case. So each case the first case will be 28.3 mole per second of nitrogen fed, and remember that the total flow rate should be 38.3. So in the first case, when nitrogen flow rate is 28.3, our initial value for acetone will be 38.3 minus pF2, which is the nitrogen feed. So this will be equal to 10, and as we go on through the for loop, we will see that the values will keep changing and we'll get different cases. And I have plotted conversion. I've created a matrix called conversion, which is the initial value minus the final value divided by the initial value, and we will make a subplot and find out what happens when the reactor when to the conversion with the volume, as well as a plot between the temperature along with the volume. All right, so okay, so let's run the code. So we'll go to editor and run this code. Let's see what we get. So there will be 5 cases, obviously. So this is the first case where nitrogen feed flow rate is this, and so we have the first case when we have a relatively high nitrogen feed flow rate compared to the rest of the cases, and we can see the conversion is almost 60%, which is 59%, and when the nitrogen feed flow rate is reduced, we have a 51% conversion, and so on. So we can see that adding nitrogen to our PFR at the inlet is beneficial for conversion of acetone and cracking it into ketene and methane respectively. Now let's look at the plot of this output. So we have a plot versus volume here from our code number 2, and we can see that we have conversion as a function of reactor volume, and we can see that for the first case, which is case number 1, where nitrogen feed flow rate is equal to 28.3 mole per second, we have increase in conversion as the volume increases, and similarly we have a decrease which in temperature with respect to increase in volume, which is of course expected from cracking reaction. So this is an expected graph. So let's move on to question number 3, which is slightly more complicated, I think, but it'll be easy. Let's move on. I'm here to explain to you guys. So we are almost done with the question. We have come to the final part of our question number 2. So in this section, we'll have to find how conversion and temperature are the outlet temperature are affected by the pressure and the flow rates and varying flow rates into the PFR. So we have an array made of pressure ranging from 1.6 to 5 with a step increase of 0.2 in between them, and we are converting into kilopascal. We have seen in the previous question that the volume range ranges from 0 and 4,
and we have varying values for Fa0, which is the inlet flow rate of acetone, and we know that the flow rate of nitrogen will be 38 minus Fa0. We have initiated this NP and NF for the loops. We'll see how it can be represented later on. And we have a conversion matrix and a temperature matrix, which we will initialize with zeros, and later on as the loop progresses we will input values into it. So I will show you guys a pictorial representation of what the conversion matrix and the temperature matrix will look like after the end of this loop. Alright, so we are using an ODE solver. Let's make it 45. Yeah, so we are using an ODE solver here, and we will obtain the final flow rate through which we will get the conversion matrix, and we will also get the temperatures of each case, which we will again see in the pictorial representation. So let's move on to the pictorial representation and see what our conversion matrix and our temperature matrix should look like. To understand what the conversion matrix and the temperature matrix looks like, I have made a pictorial representation for you guys. So as we remember, we have initialized a conversion matrix and a temperature matrix, each with dimension nf comma np. So we have a nested loop, right? So let's call the we have a smaller loop and a bigger loop. So nested loop basically means that we have a small loop within a larger loop, right? So in the first small loop, Fa0 is constant and we will have varying values of pressure. So we will through equation through line number 15, what we'll do is in the smaller loop, this will get inputted, these values of conversion. All right, and when it's all of it is used up, we'll go to the larger loop and Fa0 gets updated, and again the same thing happens, like these values get updated again and so on, and finally we get a matrix which consists of conversion values for different feed rates as well as different pressures. So we will have to plot, we will be plotting these and finding out what conversion levels look like for varying pressure and feed rates, and the same thing is done for temperature. And let's move to the MATLAB environment. So now that we have updated our conversion matrix and the temperature matrix through the for loops, the nested for loops, we'll have to finally plot them, and we'll convert pressure back to atmosphere. And in figure 1, which is the first plot, we will be plotting between pressures and various temperature levels at different flow rates. So as you can see in the legend, there are different flow rates, and it corresponds to each graph. So we'll see it after we plot it. And similarly we are doing pressure versus conversion, and each it corresponds to each flow rate, one particular plot. So let's run the code, and yeah, so let's run our final part, and let's see what kind of results we get. So our output are two figures, and this is the first figure, and we can zoom this, and it's a plot between pressure versus temperature, how the pressure and temperature varies as with respect to different feed rates. So we won't be analyzing this in depth. I think it's for some other day. When we try to optimize such systems, we will definitely analyze these systems. And so this is figure 1, and opening figure 2, we have a plot between pressure and conversion rate for various feed flow rate.
Hey, you made it this far. Good job. So if you liked our content, consider subscribing to our channel. Until then, peace.